In the common source amplifier with drain feedback, while calculating the values of C1 and C2, we introduced the concept of input and output resistances of the amplifier. Okay. Now let's go back to the original common source amplifier, the first one that we designed, with a resistive divider to bias the gate source and drain feedback resistor RD to bias the drain. So this sets the operating point, and we apply the input here through C1 and take the output through C2, and this is of course VDD, which means that there will be a supply voltage of value VDD between that point and ground. Okay. So again, for this as well, we can define the input and output resistances. The input resistance is between those two terminals across which you connect the input. The output resistance is between those two terminals across which you connect the load. So this is R out, this is R in. Okay. Of course, here this is cutting only one terminal. When it's like that, it's assumed that the other terminal is ground. Similarly here, it's between ground and that terminal. And as usual, we'll assume that the signal frequency is above a certain value and C1 and C2 are short circuits at that frequency. Okay. So if I write the small signal equivalent of this, you can do this yourself, and by now you should be quite familiar with this. We'll have R1, R2 between the gate of the transistor and ground, GM VGS, where VGS is the gate source voltage, and we have RD and we have RL. Okay, and the input is connected here. Okay. Now for the input resistance, what we do is remove the source. Remember, RS is part of the source. We remove that as well and look between this point and ground. So essentially, we apply Vtest, calculate the value of Itest, and the input resistance would be Vtest divided by Itest. Okay. Now in this particular case, you can calculate it, and it's very easy to see that it is simply equal to R1 parallel R2. Okay. In fact, this is a case where the load resistance does not affect the input resistance. This is not generally the case. When you had a drain feedback and the common source amplifier was built around that, you saw that the input resistance was affected by RL, but now it is not. Okay. So the input resistance is simply R1 parallel R2. Okay. And just as before, if you evaluate the constraint for C1, what happens is, on this side you have RS, and on this side you will have Rin of the circuit, and C1 has to be much greater than 1 over omega naught times RS plus Rin. That's the constraint. Okay. Now coming to the output resistance, we measure it between the points where the load is connected. We apply Vtest and measure Itest, and the source Vs would be set to 0, meaning it would be replaced by a short circuit. Again, this calculation is very easy. You see that because this is 0 here, this VGS itself is 0. Okay, because this voltage VGS appears across the parallel combination of these three resistors, and if there is any non-zero VGS, there will be nowhere for this current to flow. The gate is an open circuit, right? So VGS will be equal to 0, which means that this current source GM VGS is also 0, meaning it becomes an open circuit. So you can calculate this I test and take the ratio V test by I test, but it's very easy. You will immediately see that the resistance looking back would be RD. Okay. R out equals RD. So that's pretty easy for the common source amplifier with fixed VGS bias. Okay. Now typically in an amplifier like this, you would want the input resistance to be as high as possible. Okay. And then what happens is that there is no voltage division between the source resistance RS and the input resistance. Okay. And as with the case of a common source amplifier with drain feedback, the constraint on capacitor C2 would be that C2 should be much greater than 1 by omega naught times R out plus RL, because if you look at C2 on this side you have RL, and looking back that way you would have R out, whatever it is. Okay. And this is consistent with the conditions we had evaluated earlier, even before we defined the concepts of input and output resistances. Okay. The input and output resistances are quantities which you calculate for almost every circuit, because those are parameters of interest. Okay. Now it's important to remember that while calculating the input resistance, you should have the appropriate load resistance in place. The input resistance can depend on the load resistance. Similarly, while calculating the output resistance, the source resistance should be in place. The output resistance does depend on the source resistance. Okay.